All right, hi everybody. I'm Abe Davis from Stanford. This is Justin Chen from MIT, and today we're going to show you what we call modal imaging and dynamic video. But I want to preface this by stressing that a lot of what's exciting about our work is that it can and has been done with no more than a cell phone camera and a laptop. Because our critical contributions are all in algorithms and software, which we use to extract vibration frequency spectra and operational mode shapes of objects from regular video. So to see what I mean, let's start with a controlled experiment. Here we used an iPhone 6 to record 240 hertz video of a steel cantilever beam, while a shaker at the top generated white noise. And here's the video that we recorded. Now, if we zoom in, we can see that the motion of this beam is very subtle in this case. So this is a video, it is actually playing. But that's okay because our techniques have been designed to handle this kind of very tiny motion especially well. And so our software takes this video and performs a bunch of analysis, which took a few minutes on a laptop for this particular example. But the result is that we extract a frequency spectrum for the beam as well as operational mode shapes for each resonant frequency. And you'll have to read the publications that we've made about this to learn sort of how we do it, but for now, Justin will show you what that looks like.
Sure, so if you look on the screen on the left side of the screen, we have that extracted vibration frequency response, and on the right, we have a visualization of what that mode shape looks like. And so if I click on one of the peaks here, like so, you can see that you have what looks like a second bending mode of that beam. So color in this case represents phase of the motion and brightness is the amplitude. And so if I click around, look at the first mode, and don't select the DC mode, you can see that, looks like the first bending mode. If I click to the third mode, you see 2 nodal points in that bending mode. The fourth mode, 3 nodal points and 4 wiggles. And then also if I click to a point that's not a mode, you don't see anything. Cool.
So already you can see how this would be sort of a powerful tool for structural health monitoring. But we can do a lot more than just identify and visualize these modes, because after another minute of user input to set modal masses and damping for these modes, we can actually use the mode shapes that we've extracted to create a simulation of the object, which we call dynamic video. And so you're about to see is a real video of me striking the beam with a real hammer on the left next to a simulation of the beam responding to a virtual force, which we specified using an input from a mouse, just a user specified it with a mouse, on the right. And again, to be clear, our algorithm has never seen the video on the left. It only saw the white noise video that we looked at earlier. So it is simulating a response to forces that it has never observed. And then it'll show a more zoomed in, slowed down version. And you can see it's pretty close. And we can apply this to more complex objects in less controlled settings as well. So in this example, we kicked the support holding this jungle gym while recording less than a minute of regular video. And here's a recording of a user interacting with the recovered simulation in real time with a mouse. And so, this is a powerful way to reason computationally about combinations of observed modes. So for example, let's say that you wanted to know what part of the object experiences the most strain in response to a particular force at a particular point. This simulation can give you a way to approximate that based entirely on video. So finally, just to stress that this is using regular video as input, we can even apply this to video that somebody else captured. So for instance, here is a video that we downloaded off of YouTube that shows a model bridge in a wind tunnel. And by analyzing this video, we were able to find several operational modes, which are already fairly useful, but we can also use this to simulate the response of our bridge to an alien robot invasion. So to end, I encourage you to check out the related paper that we have at this workshop this year called Structural Health Monitoring from the Window Seat of a Passenger Airplane, which pretty much exactly what it sounds like. It describes how 2 years ago, flying here from MIT, because at the time I was a PhD student there, I pointed my cell phone outside of the window seat of the airplane, recorded the wing, and then we were able to recover the dominant flex mode of the airplane wing and compare it to reference to see that we got the right answer. And so with that, thank you for watching.